Hi everyone, I'm Luca Pajola and today I'm going to present you Fall of Giants, a work that I've conducted with Professor Mauro Conti at University of Padua. In this presentation, I'm going to show you the motivation that guided our research, followed by a presentation of the attack and results that we conducted on a control environment, but also on real-life applications. And we will conclude with some discussions. We all know at the beginning that the machine learning is a technology that it's deployed in a lot of real-life application, and it is used also for commercial usages. So since this is used from a very broad number of people, what about the security? We must ensure that this application responds also in the presence of an attacker. And when usually we think about the security of a machine learning application, I like to think it as a pipeline. So we have a lot of steps that we have at the beginning. For example, the data that is pre-processed by the application, and the output of the pre-processing is then forward to the machine learning model. However, the majority of the machine learning attacks so far are focusing on designing data that craft or leverages machine learning model weaknesses. However, the preprocessing is also a very sensible component of our pipeline, since if an attacker can exploit some possible preprocessing vulnerabilities, it can affect the data that is then forwarded to the model by affecting the overall model performance. So in the past, we have a few works that focus on preprocessing weaknesses. And one of these is the camouflage attack, where the attackers aim to affect and leverages on image scaling vulnerabilities. So image scaling are technologies that aim to resize the input image to resize it to a standard image size. And for example, on the left, we can see the original image, which is what we see, which is a bunch of sheep. But after the image scaling, we see a wolf. And if the model see the right image, it will say a wolf clearly, and this will lead to misclassification. So the model is not actually working properly. So can we do something similar in NLP, so in natural language processing? The idea is that natural language processing is full of pre-processing techniques to clean and prettify the text. And I was studying last year the steganography, which is the art of hiding information inside other clean information. And I found that there are some pretty particular characters which are called non-printable. So the idea is that if we insert in a text this non-printable character, when they are displayed, they are invisible because they have zero width. And so I thought that we might use this kind of characters to inject it in sentences for machine learning applications. But before describing the attack, I would like to explain why Z characters are very, very cool. They are cool because they allow us to bypass a lot of NLP challenges when we define adversarial input. So usually it's very tough to understand what we want to do, what are the operation or type of perturbation that we want to do in our sentence. In general, the modification that we are allowed to are the insertion, modification, or deletion of characters, which leads that, first of all, human can see and spot possible incongruences in the sentence. So if we add some random characters in the middle of a sentence, this can be easily spotted by human beings. But also, it is very, very easy to change the meaning of a sentence. So for example, here by just deleting one character, we change the sentence from I hate you to I hate you. And as you can see, with invisible characters, we are free of these constraints. But what might happen? So in general, we believe that Z characters can affect a lot of preprocessing techniques, but more in general, we can affect the indexing stage, which is the stage that convert the input from its textual representation to the numerical representation. And what we might find is that we can have two possible opposite model. So we have word-based or character-based granularity, which means that the type of tokens that we are going to input to the model. But further, we also use the unknown token. So when we use a machine learning model, the model has also its own vocabulary of words or token more in general that he knows. And so if there are some unknown tokens in the input sentence, we might link those tokens to a special token called ang, or we might also just discard it. So we have four possible combinations. And if we insert the Z character inside the word love, we might have in the word-based models that the sentence completely change its meaning, or in character-based model, vice versa, we might have an increased noise of the sentence if we consider ang, or the sentence is maintained. So character-based without unknown are resistant to this attack in general. About the attacks, we conducted our experiment in the area of hate speech evasion. So this is a very popular topic in NLP. We identify with an algorithm negative words inside a sentence, and we inject Z characters inside these words. There are two possible injection strategies. So the first one injects only one malicious character, and the second one injects multiple malicious characters. In the control environment, we present the four possible models that I just described a couple of slides ago based on a GRU. The dataset is a sentiment analysis dataset, and the goal is to evade negative sentences. So on the figure, I'm reporting the misclassification percentage at test time of this negative set of sentences. We may notice that it's very easy to see that word-based model tends to be more vulnerable to Z attack, while character-based model are more resistant. Moreover, this is also intuitively to think that the more noise we inject on character-based model, the higher the misclassification percentage. But now let's go to something more cool, in my opinion. So the question is, do also real-life applications are vulnerable to this attack? So we conducted our experiment on 4 top brands: Amazon, Google, Microsoft, and IBM. And we tested a lot of different services, from translators to sentiment analyzers. And among 12 APIs, we noticed that 10 are vulnerable to our attack. And for example, here Google Translate translates I want to kill you to I love you, which has a completely different meaning. We are gonna to show you here on this presentation only the case study of the sentiment analyzer, where on the real corpus, we can see that the negative sentiment distribution is close to 1. While when we inject Z characters, the distribution goes close to 0. So it means that the services are vulnerable. And here we might notice that 3 out of 4 services are vulnerable to the attack. The implication of our works are, I think, very important, because we first of all prove that the preprocessing is a very sensible part of machine learning application. And we also tested in real life condition by showing that a lot of APIs are vulnerable to our attack. We believe that this work should motivate future researchers to focus and to study the security of machine learning from not only the machine learning model perspective, but by considering the whole machine learning application, so also the preprocessing stage. Thank you for your attention.